let me just start over because I forgot to start the recording once again. All right. The reason why I started recording sort of after I started the stream itself is because I don't want to edit these videos. I want to put them out just the way they are. All right. So, yes, like I said, my daughter is home with me right now. We found out this morning that she had a slight fever. And so my wife gave her some medicine to a pill to take a little bit the top of the fever, and then she stays home with me. So I must say, unfortunately, this COVID business has come a little bit too close to comfort for me. First my daughter in first round, and then my son in second round, and now my daughter has a fever. We don't expect it to be COVID or coronavirus because she don't have all the symptoms. For instance, she doesn't have a sore throat of any kind. I'll be right back. All right, so yeah, this lecture is fortunately not going to be that long as far as I can see. That's a good thing in the current circumstances. But I want to say that, yeah, this COVID business has come way too close for comfort for me. I'll be right back. Back again. Yeah. So we found out this morning that she had a fever, and we did what we could do. And I took her to get tested for coronavirus today, a little earlier today. So everything has been sort of thrown up into the air and down again, and problematic, you know. So I will say that if you can hear someone in the background either yelling at me, uh, giggling, or sniffling and coughing, that's her. She'll do all the above because, well, she's ill, like I said, but she's also watching YouTube on her iPad, so she sometimes finds something she finds really funny. So, yeah. Today, like I said, it's going to be a relatively short video lecture. Let me see if I can move the camera a little bit, like that. You can hear in the background right now. Yeah, so that's basically it. I hope that's okay. Also, I am sorry that I haven't put on the former lecture, the introduction, on my YouTube channel. I will do that today when this lecture is finished. So today is going to be about basically what you can do if you want to observe today. I mean, if it's nighttime, right? But today, what can you do, and how do you find your way around on the night sky? What tools do you have that you can use, and all those sorts of things. And I want to show you the book that I recommend you get. I will use illustrations from it and all that. Some of them will be from the Danish one, and I'm sorry that that's just the way it is. I couldn't find some good ones in this. Most of them should be from this one. So like I said, it's the book called Universe. Yeah, you can see it. Universe by Friedman and Kaufman. It's the 8th, let me see, they should be able to see it. It's the 8th edition. You can buy it still, I think. Not sure if you can get the paper, the 8 editions, but you can buy Universe, this book, as a paper version if you want that, both hardback and softback, I think. That's up to you, but I do know, at least when I last looked, it has been a while ago, I must admit, that you could find the 8th edition as a downloadable PDF file that you can get. So this is the book that I use. If you are from Denmark and you're watching these lectures, then you can use, like I said in the last lecture, the book called Det levende univers. It's also a high school level book. This book here, Universe, is a little bit above. It's sort of more like college level, early college level. It's still very, very much introductory, but just like any other lecture book we get from the United States, they really use a lot of pages to explain the same thing, which is a good thing, in my opinion, especially for someone like me. I like to read a lot about it to make sure that I've fully understood it. But compared to Danish books, there are many, many more pages in these lecture books here. That may be a good thing for you. It may not. Depends on your reading style and what you like. All right, so let me switch to the my screen here, so you can see the you can see my screen. Well, at least one of them. I have two. That's why I keep looking to this side here. I have my OBS studio and all that over here, and then I have my webcam, my phone actually, right down there. And my primary screen is right in front of me. All right, so let's get started. Let me just make this full screen mode. All right, so today we're going to look at, and the next couple of, I think it's 5 or 6 lectures, we're going to look at the solar system and the night sky. So it's very, very basic astronomy. Right. Wanna become famous by followers, primes, and viewers on bigfollowers.com? Huh. No, thank you. Not exactly a a question. So I won't do that, sorry. Yeah, let's get started. So the solar system and the night sky is basically going to be about what can you do as a person right now. Well, like I said, if it's nighttime, but right now to tonight then. What can you do in order to observe? What tools do you have, and what can you, how can you find your way around on the night sky? So I basically just repeated myself. Let's get started. Like I said, it's on November 26th here, and let's get going. So this is going to be very introductory, finding your way on the night sky. There are some programs that I would recommend you get for the entire course, actually. Some of them will be using more than others, but and some of them I will recommend you use on your own hand. I will, if it's required, if you want me to, I can give you some slight introductions to yeah. to the programs themselves. I think a Stellarium is definitely going to be something that we're going to use if we get into, there goes the webcam. 2 seconds. All right. Let's see. So let's try. Auto, perhaps? No? Oh, that was. It found out on its own somehow. Let's see if I can make it focus on me. Hopefully. Let me just get the... let me move it a little bit out of the way so I can see. Let's get the cam screen. Yeah, I seem to be pretty much in focus, so that's okay. All right. So yes, if you want help in these particular programs, I can do it, but basically, I expect you to use Stellarium on your own hand. I don't want to go much into how you use the program because honestly I find it to be very simple. You simply just click and move your screen around. That's it. Say your image DS9. If we get to talk about FITS files, for example, if you do images as an amateur astronomer, or if you download FITS images, professional images, we can use DS9 to watch it. And it's not Star Trek DS9. It's a program to watch these files. And finally, I would also recommend that you get Python version 2.7. That's what I use. There is a newer version called 3.1, I think it is. But I'm still stuck with the 2.7 because I just like that version. That's it, simply. And I would recommend that you get these packages here, Matplotlib, NumPy, and Skippy. I'm not sure what you would call it. If there's time, I can give you some tips and pointers in how to install these. But generally, I would actually expect you to find the stuff on YouTube and get the help from there. It's not certain that I will get into this with you, but these are good programs to plot simple stuff and get illustrations and all those kind of things. So yeah, that's what I would recommend you get. And if you want to download, you can go into Stellarium. You can get it at stellarium.org, and you can find your version for the system. If you have a 64-bit version, OS operating system, I would highly recommend that you get that. And I would expect that most people actually now get has 64-bit versions. So yeah, get that. DS9 should be you should be able to get it at this webpage here, ds9.si.edu-site-download.html. And again, find 64-bit version if you can, if your operating system it's a 64-bit version. And an alternative to Stellarium, which I will not recommend you get, is called Carte du Ciel. I'm not good at French, so if I slaughtered that name, sorry. In English, we call it SkyCharge. It's a more resource-friendly program, meaning that it doesn't have nice visuals like Stellarium, but it can also be quite overwhelming because honestly, it looks more professional, it has more options, and it requires you to know what to do with these options in order to really use it. But if you will, and you want to learn it, it's a good program if you want to control a telescope with it. Like, for instance, I have I think in US it's called the Skywatcher Atlas Pro. Here in Europe it's called Skywatcher 6 Pro, something like that. I can't remember the name actually. But if you want to control the telescope like that, then Carte du Ciel or SkyCharge is really good for that. And you can download it here at www.ap-i.net/skycharge/en/download. So that's where you can get it. All right. Now that we have all these sort of formal things out of the way, let's get into this. Let's get familiar with the night sky. So when we talk about the night sky, if you want to go beyond just go out and take a look around, but you want to notice where stuff you find, and more importantly also, if you want to tell other people of what you have found and where it is and how you can watch it, then we use something called angles and angular size. So angles and angular size is basically the same thing. So for instance, if we take, for example, from the horizon and you look up straight in the vertical line, that will be 90 degrees up. So you can sort of imagine that we have 180 degrees around the way we look, because, well, what is below the other 180 degrees is not that interesting. because then you would just be looking down into the ground. That's one thing. That's, for example, you could say, well, I watched the sky, a star around here that was about 45 degrees up from horizon. So you can inform someone else about where that is. Now, you can ask yourself, all right, why do we go only from 0 degrees, which is the horizon, up to 90 degrees? Well, that's because you have to imagine that this is sort of one direction. So we have two directions that we can orient ourselves on the sky. We have sort of the horizontal way to look around, and we have the vertical way to look around. And we will call that altitude and azimuth. It's one way to look at it. We also have another that we're going to discuss, which is called rectascension and declination. So that's one thing, to know where stuff are. We can say roughly at what degree altitude and what degree azimuth. This is azimuth, by the way. There's another way, and that is to discuss the angular size. So for instance, the moon that we can look at often, the full moon that is, has an angular size of about a half a degree. And so in order to know what this is all about, we divide degrees into certain subparts that we're going to discuss further on. But for instance, you can say that, well, the angular size of the moon is a half a degree. You can also say the angular distance between two pointer stars. In this case, they have taken the Big Dipper, and they say that between these two stars here, it's roughly 5 degrees between them. So that is roughly 10 times the angular diameter or the angular size of the moon. And finally, if we take this is the north celestial pole. If you take the south celestial pole, we have the Southern Cross. And the angular size between these two stars here is roughly 6 degrees. So that is, what about 11 times, roughly? 11 times the, no, 12 times, sorry. Yeah, that's 12 times the, 12 times the size of the moon. So you can take the moon and then you can fit it in between here 6 times. So in order to figure out how big things are, or what the difference in distance between them, you can use your hands to sort of find your way around. So if you take your palm and you hold it up and you need to have your arms stretched out. So roughly the size from one side of your palm to the other, when you have your fingers stretched out, is roughly 10 degrees. If you take your, I think it's, not sure what it's called, the index finger. If you take that, and then you, the width of that finger is roughly 1 degree. And then if you take again your index finger and you twist your hand around, then the first part of your finger is roughly 3 degrees. The second part of your finger is roughly 4 degrees. And the third and final part of your finger is roughly 6 degrees. So that's different ways. And again, remember, you need to have your arms fully stretched. Otherwise, this won't work. If you take it close to you, then, then you will skew the results. That it won't be bigger. This will get enlarged in size. You'll cover more. Sorry. Yeah. But as you probably can imagine, hopefully, I suppose, many of the things that we watch in the universe is actually much smaller than the moon, for example. The moon was roughly all the distance between stars. We have components in the interstellar, in the universe, in our own galaxy, that is, when you observe them, much smaller than 1 degree. And so in order to figure out how to report those measurements, we have astronomers has decided that we sort of subdivide degrees. So if we take 1 degree, we say that we subdivide that degree into arc minutes, and we then take arc minutes and we subdivide those into arc seconds, and they are usually abbreviated by this symbol here. So you know the degree symbol, that's the circle here. And then with arc minutes, you have one of these. And with arc seconds, you have two of these. So that's usually the way it's written. So if you look at some popular article, or mainly it's probably going to be more professional articles on astronomy, and you say, well, we found this and it had a width of 120 arc seconds, then it would be, or 5 arc seconds for that matter, it will be these twos here. And if they say the total width of our image is 2 arc minutes, you see one of these symbols here, then it means that it's arc minutes. And we subdivide them so that 1 degree is 60 arc minutes, while 1 arc minute can be subdivided into 60 arc seconds. So you can imagine that 1 degree must be 3,600 arc seconds, because 60 times 60. Yeah. This is one of the images that we have from the Danish book. So obviously this is the Earth. In Danish it's called Jorden. And here we have the true position of the star. And here we have the position of the star on the celestial sphere. And here we have the celestial North Pole, and this is the celestial sphere, and all of those things. So we can subdivide positions on the night sky into positions on this celestial sphere here. And so you have to imagine, which we're going to talk about a little bit later, that all of these points here on the sky is divided into a coordinate system. So that's the way we can find our way around. And when we observe something on the night sky, because the Earth is rotating, they will always seem to transition to the west. At least that goes for things you observe at the equator. Things that you observe higher on the Earth, on the night sky, will seem to go in sort of arcs from east to west. So you can ask yourself, why do we even have a changing night sky? Well, obviously there's one reason, that's the sun. So let's say, for instance, that we have the Earth at a given point in time. At that point in time, we will have a day side, which is illuminated by the sun, and we will have a dark or a night side that will be not illuminated by the sun, obviously. And so the rotation of the Earth is this way around here, so you are sort of watching the Earth from the North Pole and down. And so in this case, for instance, you can say we have a person in California at 8 p.m. local time. He could be watching the constellation Cygnus overhead, as it's seen from California, and then he can also see the constellation of Andromeda. If we then go a little bit further in time, we could say, well, that same person in California at midnight time will no longer, well, he'll probably still be able to see Cygnus because it's pretty high up. It should be circumpolar for even someone in California. But at midnight time, Andromeda instead will be overhead, sort of directly over his head. And that's because the rotation of the Earth. And obviously when that person in California goes into the day side, he can no longer watch any constellations at that point. So another thing is that because the Earth is not only rotating, but is also revolving around the sun, we can see different things on the night sky because of that. So for example, be right back. let's try that again. Sorry about that. Well, like I said, because the Earth is revolving around the Sun and is rotating around itself, we will have, for example, Earth in July. You'll be able to see, for example, at some point you will be able to see the constellation Cygnus sort of directly above. And then later, for example, in September, you'll be able to see sort of that will be, I would suppose that would be midnight because of the position it is. It doesn't say on the figure, but at midnight, you will be able to see, in July, you'll be able to see, well, it's not very accurate, right? But try to follow it anyway. In July, you will be able to see Cygnus sort of roughly at midnight. In September, you would be able to see the constellation Andromeda directly above at midnight. And in November, for example, you will be able to see the constellation Perseus directly above at midnight. And I expect that they are still talking about this person in California and not me in Denmark. Let's go on. So, because the Earth is slanted, if you imagine, we're going to talk about this more when we go into sort of solar systems themselves. But if you imagine that when we look at the solar system from the side, you can sort of see for yourself that all of the planets seems to be sort of in a line. And it's basically the thing that you can see here. This is wildly exaggerated because the Earth is only slanted around 23.5 degrees, I think it is. But if you imagine sort of taking a line through all of those planets, then you can have sort of a plane in which all the planets roughly lie. Again, seen from the side, and the slantedness, the slanting that we usually talk about when we talk about the Earth is always with respect to that plane inside the solar system. We're going to talk more about that when we sort of talk about the basic parts of a solar system, any stellar system with planets actually. But we have some stars that never rise and never sets because of the rotation of the Earth and this slanting of the Earth. So, for instance, if we have this guy here standing almost at, he's at the 35 north latitude. So, the north celestial pole is 35 degrees above the northern horizon, and the south celestial pole will be 35 degrees below the southern horizon. So that means that all the stars that we have within these 35 degrees at the southern pole or southern hemisphere part, they will never rise. As you can see, all the stars within this circle here will never get above the part that he will be able to see. And likewise, we have these stars up here that is, well, they are 35 degrees above the horizon. They will never set. And so any other star that you have on the celestial pole, the north celestial pole for him, they will rise and they will set. But these in here will not. And we call them circumpolar, meaning that they sort of revolve around the north celestial pole for him, so that he will be able to see all of these stars at any time during the entire night. Because the Earth is slanted and because it rotates around itself, there is, and again, I assume when they say us in this book, they're talking about California, but we have sort of certain ways to deal with how we would look at stars. So, for instance, at a given point at California, if you look at the stars, they would be moving sort of in this direction here, slanted. If you were at the North Pole, because then the Earth would be rotating you would be rotating almost like a spinning top, then stars would be almost, they will look like they will go sort of sideways compared to you. And if you were at the equator, then the stars would go up directly above you and then back again, set behind you. And as far as I know, all the stars that you can see, well, it gives itself right, almost all the stars that you can see at the North Pole will always be circumpolar, because they never set and they never rise. And all the stars that you can see on the equator will never be circumpolar, because they will always set and they will always rise. Perhaps even with the exception of the North Star. That will probably be the only star that could really be seen as circumpolar. At the equator, that is. So let's talk about that. Let's talk about the North Star. How do you find the North Star? Well, there are several ways that you can do it. Me personally, I find the easiest way to find the North Star is to find Ursa Major, or the Big Dipper. And it looks like sort of a wagon with this, this is the wagon, and this is sort of the lead to the horse or whatever it is. And then you take the back part of the wagon here, these two bright stars here, and then you sort of double them. I think it's about 5 or 6 times, and then you can find Polaris, the North Star, which is also a part of what is called Little Dipper or Ursa Minor. Later you're going to know, well, you're going to know now because I'm going to say it, but Ursa Major is called the Big Bear, and Ursa Minor is called the Little Bear. So they are actually not wagons, they are animals. But you can also go a little bit further than that if you want to find, be sure that you can find the North Star. And this is also a great exercise in performing what some people call star jumping method. Other people will say that it's sort of a way to sort of try to navigate your way around on the night sky. But nevertheless, the first thing you will, in this case here, will try to find is going to be the constellation of Virgo, which is the Virgin. So I just saw that there was an outfall in the connection, so I'm going to start over again with this. If you want to figure a way figure out a way to find your way around the night sky, like I said, you can use my preferred method to sort of just find Ursa Major and then find the Polaris, the North Star. But if you also want to sort of try to train yourself in a way to sort of find your way around and navigate on the night sky, you can do like they suggest here. So you start by finding Virgo, which is the Virgin. And you'll find the brightest star in the Virgin, which is called Spica. And then you sort of take an arc all the way up to Bootes, which is the Hunter. And there you find the brightest star there, which is called Arcturus. And then you sort of follow, you can almost imagine that you follow this line here from Spica, so this way, just like this. Then you find Arcturus, and then you sort of follow these 3 brightest, the Arcturus and the 2 other bright stars here. You follow them sort of roughly in a slanted way until you get to the outer part of Big Dipper, or Ursa Major. And then you just follow that constellation all the way back here, and then you do what I just said. You take the back part of the wagon, if you will, and then you sort of multiply it in the same direction. You can also just say that this is a pointer. So you look like this, and then you get to Polaris. Now, they say that north is exactly at the North Star. That is not completely accurate, but it's close enough. So that's one way, and the good thing about this, there's several good things about doing this. The first thing is that you get practice in finding your way around on the night sky. And that is a good thing to sort of get an intuitive feeling about, or sort of, getting intuition in how the night sky is. Let me just close the door a little bit. because for some reason she has found her energy now, so now she's really noisy. There is value in finding a way for yourself to find your way on the night sky, so you get an intuition on where things are, and remember that a good thing about having this intuition from where you live is that if you move significantly on the night sky, well, on Earth, then you will get a different night sky. For example, I live in Denmark, so we are pretty much very close to relatively close to the North Pole, right? It's pretty okay. And we have a certain night sky. For example, all of these, I'm pretty sure that Botis is also, but definitely both Ursa Major and Minor are circumpolar at where I live. And then here, a couple of years ago, we were on a vacation to Italy, and we were a couple of kilometers, 50 kilometers, something like that, from Rome. So that's sort of the middle Italy. It's a significant move towards south, but definitely towards the equator. And so the good thing about having an intuition on where these constellations are and how you find them, all that, is that when you move such a significant part on the night sky, you'll be able to find the things that you know. You'll be able to find that. And then you can use that to sort of navigate your way all the way around to the stuff that you don't know, because you can now see some new constellations. So that's one way to do it. Another good thing is that if you buy a telescope like the one I have, oh yeah, and I remember, in Denmark, in Europe, we call it the Skywatcher EQ6 Pro. So if you buy a telescope like that, or basically any telescope that is computer controlled, you will usually have to sort of align this telescope with some stars. And it will not tell you where those stars are, it will only tell you what the name is. And so a good thing about knowing these stars and having an intuition on the night sky is that it will make this alignment much, much, much faster. All right, let's continue. So again, we have some sorry, we have some parts from the Danish version of the book. So if we look at the North Star, you could say that the height of the North Star over the horizon in degrees is the same as the latitude. So for instance, if we live here, I think it's at 53 or 51 degrees latitude. It means that the North Star where I live will be around 50 degrees above the horizon. And that it certainly is, because I've aligned my telescope towards the North Star. So you can see here, for example, here we have this degree here. This is B. So for instance, in this case, we could say that B is, well, let's just say it's 51 degrees. So I would live, well, that is definitely not 51 degrees. It's more like, let me see, this is 0, so it's roughly, it's 45. So let's say 20, 24 something, 22 degrees. 21, 22.5, something like that. 22 degrees, let's just say that. And then if you measure, you look up at the North Star here, if you measure that compared to the horizon that you see, then this distance here, or this angle here, will also be those 22 degrees. And you can see for yourself that that is accurate. For instance, let's take the extremes. If we look at B at equator, that is going to be 0 degrees. Since the horizon here is like that, and the North Star will be here, then this angle here will be 0 degrees. The other extreme is, what if we were at the exact North Pole? Well, at the exact North Pole, we will have 90 degrees latitude. Well, because we have the horizon here and the North Star will be directly above, that degree will also be 90 degrees. So that's one way that you can sort of convince yourself that this is the case. And this over here is sort of just an image that you can use because the Earth is rotating. So the Big Dipper will be, or Ursa Major, will be at different positions on the night sky, but they will all be revolving in the same direction around the North Star. That's just what it says. So let's get going with the coordinate system, because if you want to tell someone where you have found this brand new cool looking comet or asteroid, then you need to be able to say to someone, well, where is it? And one way to do it, of course, is to use the constellations and say, well, I found it sort of a little bit above the constellation Taurus. Then the person that you're talking to would be able to go out in the night sky and then look at find Taurus and then look a little bit above, and maybe he will be lucky enough and find it. Maybe he won't. So one way to do this more precisely is we divide the night sky into positions of rectascension, called alpha, and declination, which we call delta. And so the way that you define these coordinate systems on the night sky is that you find the point on the equator, or this middle part of the celestial sphere, at I think it's called the spring equinox. The position of the sun in the spring equinox is what we define as 0 in rectascension. Now, rectascension, that means that it's 12 o'clock, because we divide rectascension into hours, minutes, and seconds, and we divide the declination into degrees. So obviously you can see it here. We have, again, from 0 up to 90 degrees, that's the declination. This would be minus. I'm not sure whether people on the South Celestial Sphere will do it the other way around, so they will say this is positive and this is negative. Doesn't matter, but most people has fortunately agreed that this is the way that we define it. So from the celestial equator up to the North Pole, on the North Celestial Equator, is positive degrees, and from the celestial equator down to the South Celestial Equator is negative degrees. That's just the way it's defined. But as you can see here, it gives you an very good opportunity to say, well, now you can tell your friend, let's say that this was the comet or the star that you found, then you can give him exactly the position in rectascension and the position in declination. And that means that if he has a telescope, a computer, especially if he has a computer-controlled telescope, he can point that telescope, if it's aligned, of course, at these exact coordinates, and then that whatever it was that you found that you want to share will be exactly there. It's more precise than just say, well, it was sort of a little bit left to Taurus or Virgo or whatever it can be. But you can give the exact position on the night sky. So we use rectascension and declination. And like I said, we divide rectascension or alpha, we divide that into hours, minutes, and seconds. So that means it goes from, well, 12 o'clock, 0 hours, 0 minutes, 0 seconds, all the way up to, well, you can also say 24. Some people use 24, but it goes all the way up to 23, 59, 59 in respectively hours, minutes, and seconds. And again, as you can see here, we have, it's the vernal. Yeah, of course. Yeah, it's vernal, but spring. Vernal equinox, that's the 0. That's defined as 0. And then we have this it's called right ascension. That's why it's called rectascension. It's right ascension, so it turns to the right. And then we have angles of declination, and obviously they goes from minus 90 degrees all the way up to 90 degrees. There's a very precise coordinate system to find your way around on the night sky. So we also use another terminology. It's called when something is culminating. And that means that it's on the highest point in the night sky. So for instance, if we have North Celestial Pole here, we have Zenith here, and we look at something, then this star here will be culminating. It's at the highest point at the night sky. So it will rise, culminate, and then go back again, called set. It will set. And then again we have, well, as you can see, in this case here, we have a culmination of something that is not circumpolar, something that goes up and goes down. But what if it's circumpolar? Well, then we use another terminology, and that is still culmination, but then we say, well, when the star is at the very lowest it can be, it is at its lower culmination. And again, when it's at the highest point it can be on the night sky, it's at its highest or higher culmination, upper culmination you can also use. Alright, so constellations, we're going to talk more about constellations. I would like for you to be able to identify a handful of constellations on your own hand. And obviously, as always, if there are questions, then you can send it to the mail that I presented to you in the first lecture when I put it out, of course. And else you can write it in here in the comments, but please keep it to the subject at hand. Not like someone called New Legendary 15 something. Yeah. All right. So let's go on. So we have three ways of sort of defining culminations. We have what is called observed, then we have the scientific, and then we have the classical. Let's start with the classical. The classical is really what gave rise to the names that they have now. For instance, here we have Orion here. Here he has a club. Sometimes he has a sword. And he has the lion skin. Sometimes he has a shield, I think. And then he has his belt here. And he is ever hunting the bull or Taurus, the bull. So this is all the way back to the classical area, the classical era with the Greeks, the old Greeks. In science, well, we can't really use these figures for anything. In science, I mean, of course, astronomy and scientific astronomy. We don't really use these figures here because what the heck would they? Well, we have this under what I mean, what do we use it for? So instead we say, well, we have sort of the area that, in this case, Orion sort of expands over. And then we put a limit on, sort of a boxy limit all the way around this area here. So in science we say, well, if we find something and particular, a new supernova or something like that, and we say it is found in the constellation Orion, it doesn't mean that it's somewhere within this figure here, his belly or anything like that. It simply means that it is within this yellow square here. And you can, for example, see over here we have Gemini, the twins. They are sort of this area here. We have the Crab Nebula up here. We have Taurus here. So for instance, the Crab Nebula will probably say that it's within the constellation of Taurus. The Great Nebula here, it's also called the Orion Nebula. It's obviously within Orion. And the star Betelgeuse or Bellatrix or Rigel or whatever it is, they are within the constellation of Orion. So that's the scientific way of looking at constellations. And finally, because we have the way that we all know, we go out and we look at the night sky. And when we see the constellation Orion, this is what we see. So there's obviously, well, not all of these stars, but we see sort of the brightest stars. And we can also see the Great Nebula. if you look very closely. But that is the way we see things. So obviously there's also the observed part. So on the northern hemisphere, we use something called the summer triangle to sort of get away. It's another way for you to sort of orient your way on the night sky. So the summer triangle goes from Deneb in Cygnus. Here it's called the Northern Cross. In Denmark, and I think also most of Europe, in Scandinavia, we call it the Swan, because as you can see, we have the tail here, the wings here, and the long neck here. We also have Lyra, the Lyra, with the brightest star called Vega in it, which you have up here. And then finally we have Aquila, which I think is called the fish or something like that. And we have Sagitta here. And the brightest star here in Aquila is called Altair. So the summer triangle is all that is within Altair, Deneb, and Vega. And this is a pretty vast area that you can see to the east, of course, but nevertheless. So you can sort of use this summer triangle here to find other stuff on the night sky. We also have another just defined to winter instead, called the winter triangle. And here, for example, we have the twins, Gemini, with Pollux and Castor. We have Auriga, I can't remember what that is, with Capella, which is the brightest star. We have the bull, or Taurus, with its brightest star here, Aldebaran. And then we have what we talked about before. We have Orion here, which with its brightest star, Betelgeuse, up here. Then we have the big dog with its brightest star, Sirius. And then finally we... yeah, I'm sorry. But we have the small dog here, Canis Minor and Canis Major, with its brightest star called Procyon. So the winter triangle is everything that is in between Procyon, Betelgeuse, and Sirius. And yeah, I know that these names are widely exaggerated and really, really silly because, I mean, seriously, 2 dots, small dog, tail and butthole? I'm not sure about that. All right. So I guess this is, let me just check. No, almost. As you can see, we have sort of 2 things that we can sort of define as, let me go back just a little bit on the, there. Because we talked about before that the Earth is rotating around itself, but it's also revolving around the Sun. Now, if we look the Earth in itself, just look at the Earth itself. From that point here, and one rotation, takes exactly 24 hours. But, and if the Earth was standing still here, if we could sort of stop it from revolving around the Sun, then one whole day would take exactly 24 hours. So from daytime to daytime would take 24 hours. But it's not. The Earth is rotating around itself, but it's also revolving around the Sun. So that means that while it is rotating like this, it has also moved a little bit in this direction here, meaning that the time it actually takes from daytime to daytime is not exactly 24 hours, but what we call sidereal day. And one sidereal day is actually 23 hours, 56 minutes, and 4.1 seconds. While an ordinary day is 24 hours, like I said. And they are both measured in 24 hours intervals. So sidereal day is usually the sidereal time is actually usually the time that astronomers use, because it gives us a very big advantage. But what you can go into these two web pages here, www.jgeeson.de/astro/astrojs/sidereal clock, or you can go into www.astrouv.edu.pl/jscowron/radec/. And both of these should give you tools to sort of play around with the difference between sidereal days and ordinary daytime. So why is it that sidereal days is so important for astronomers? Because, I mean, what the heck? What is it? 4 seconds? I mean, seriously? The thing is that direct ascension tells us the best time to observe in sidereal time. So that means that if something has a certain position in direct ascension, it tells us exactly where it will be as the angle above the horizon, which is the delta. So let's take, for example, the star Spica. It has the coordinates alpha, 13 hours, 24 minutes, and 11.6 seconds. I'm sorry, I put in a Danish word here. It should say and. The delta, the declination, is minus 11 degrees, 9 arc minutes, and 41 arc seconds. So that means at 13 hours, 24 minutes, and 11.6 seconds, this star here will be at minus 11 degrees, 9 arc minutes, and 41 arc seconds at its highest. Now, obviously, you would need to know what is, because this doesn't mean that you can see it at 13 hours, 24 minutes, and 11.6 seconds in normal time, right? Because there's a difference between the sidereal day and the ordinary day. So that's why you need these converters here to tell you what a certain given time in sidereal day is in our ordinary clock. But it gives you a very good opportunity to figure out when it's best to observe this. And obviously, since the star is at minus 11 degrees, it will at this point be at its highest at the south celestial pole. That's the way it is. But because it's minus 11 degrees, that doesn't mean that you can't see it here on the north celestial pole. It just means that it won't be visible for very long. Alright, that's it. Like I said, if you have any questions, then you're very welcome to write comments here. I didn't get anyone this time. But hopefully I can lure more people into these kind of lectures here. Because one of the reasons why I went online on Twitch to make these lectures instead of just putting out YouTube videos is that I want to have sort of an ongoing debate with you, the watchers, and you can ask questions and we can have a conversation about the subject instead of just like me and just like this time and the last time that I just babble my way around it. But if you have questions, if there's anything you are in doubt of, if there's something else that you would like me to explain at some point, so I can sort of correct my lectures for that. I can't promise that I will do it, but if you have questions, if you want to, then I can go in with that. And then I would also like to say that I have thought about making sort of a astronomy science podcast, something like that, on this very channel here, where I pick a couple of articles that I find to be very interesting about astronomy and physics and all that, and I will try to get all the articles that I get from arXiv, so that you will be able to read them as well. And then I'll try to sort of break down the gist of the articles for you, so tell you what is the basic part of this, why is this interesting, and so on and so forth. But nevertheless, I hope that you have learned something. Maybe you even enjoyed this video, but I hope that you have learned something about it. I would very much like for you to, when you have watched this video, that you sort of break out an atlas of the night sky, and then figure out what you would like to go out and watch on the night sky tonight, perhaps even, and definitely try to get Stellarium, because it's a really useful, very direct and visual tool that you can use to find your way on the night sky. You can actually all of these exercises that I've sort of given the introduction to here, that I would sort of hope that you would go out and do. You can do all of those with Stellarium. Obviously, I find it to be more fun to do it in the night sky, but if it's overcast or anything like that, you can't do it. There is one thing that I would like to warn you about, at least here in Europe, in Scandinavia. But let me just get some things. 2 seconds. All right. So a while ago, when I sort of started my journey into amateur astronomy, there was one thing that quickly became very popular. If you have attended lectures at high schools, or perhaps even more in college level thereabout, you will often see teachers running around with this laser pointer to point at slides, and it's very, very handy because I can use my mouse here to show you what I find to be important. But if you're standing on the floor at a lecture hall or at a classroom, you can't always run up to the computer and move the mouse around, because that would be unhandy. So and that's why teachers often use these laser pointers, and they also have sort of the mouse buttons at their hands so they can change slides. They can do all of these things. A couple of years ago, I think it's about 10 years ago, something like that, perhaps a little earlier. Let me see what it says in here. 2007, so yeah, it's more than 10 years ago. These laser pointers here became very popular because they are very powerful, as you can see, extremely powerful, and they are very good at when you want to point out stuff on the night sky. They are actually to say, well, you have a star here, and you can look at that, and then you can sort of flip that around and you can point at different places. It's very handy because it's a very powerful little laser that you can have in your palm. The problem was that it actually could blind pilots and sort of confuse them when they flew around. And so that was why they, at least here in Denmark, but I also think that perhaps in most part of the world, well, no, the US, you're very liberal about these these things, but at least in most of Europe, I think these are banned, so you can get fined if you use them. So I just want to sort of implore you that if you want to use these things to sort of point to others on the night sky where things are, then at least be careful, because you can actually end out having a pretty big fine to pay. All right, yes, I hope that you have learned something from this lecture. I really do. And I also hope that you perhaps even have enjoyed yourself a little bit. I know that the circumstances is that the way they are. I have a sick, ill child at home, so it gives some noise. But nevertheless, yes. And I hope that I will see you in the next video, the next lecture. Hopefully it will be more, so I can get more questions. We can get a dialogue going. And hopefully I can, the idea really is that I want to show you how incredible and fantastic the world of astronomy is. All right. Hope you enjoyed this, and I will see you in the next one. Bye-bye. Oh yes, remember, really, really important, you can always, well, when I upload them, of course, you can always go back into the YouTube channel called Mike's Observatory, just like this, without the X's. The X's is just because I had to put them in. You can always go back to the channel called Mike's Observatory on YouTube and rewatch all of these lectures. I have a former lecture set that you can also watch if you don't want to prepare yourself, but I will try to update this. It's a while ago since I made them and I didn't finish them. So yeah, remember that, and then I will see you in the next one. Bye. And be safe out there. Of course, be safe. Very important. Bye bye.